All right, hey everybody. So we have already talked a little bit about parametrized surfaces and about how we can construct them out of these coordinate patches, which come from a given parameterization from a map in some subset of R2, which we usually denote as U comma V space. We've also talked a little bit about the tangent plane to a given parametrized surface at a given point and how we can construct that. Today, we're going to look at a very related idea, and this is the idea of perpendicularity. So not just a tangent plane, but we're going to be looking for a perpendicular vector to the surface at any given point. And we'll call this the normal vector, right? And so this is our general setup, right? We have a coordinate, we have a coordinate system. We have a subset of R2. This is the set U here. And let's say that we have a parameterization X that maps this to this set here in R3, this parameterized surface. And let's also say that we're going to focus on a particular point on the surface, this point P. And let's pretend that P gets mapped to from the point Q back here. So X of Q is equal to P. Well, we've already seen that we can create our tangent space, right, our tangent plane, to this surface at the point P by doing the following, right? We can look at our point Q, and we can think about taking a derivative in the pure U direction. And let me actually shrink that down just a little bit. We can take that in the pure U direction. We can also take a derivative in the pure V direction, and the result, if we map it into this space via the differential, will be a vector of the form X sub U. That's the partial U derivative of our parameterization, right? So X sub U at the point Q, and that will be, say, this vector right here. If we do the same thing for V, right, taking a derivative in that direction, we get X sub V at the point Q, and then that becomes this point up here, or that vector up there. And both of these vectors lie tangent to the surface, right? So if I take the span of these two vectors, right, any linear combination of them, they sort of define the directions of my tangent plane, right? So once I've determined my vector X sub U and my vector X sub V, they're determining my tangent plane, right? And so this gives me this tangent plane here, which we've been calling T sub P of S, so the tangent plane to the point P of the surface S. Now, we are interested in using that information, or using some of that information and going beyond this to construct a vector that is perpendicular to the surface. And the observation that we make is that any vector that is perpendicular to this tangent plane will be also perpendicular to the surface. And that's true by virtue of the plane itself being tangent to the surface, right? So if this is my surface and this is my tangent plane, anything that's perpendicular to my tangent plane will also be perpendicular to the surface itself. So I simply have to find a vector that is perpendicular to this tangent plane. But in that case, we're actually in luck, because here I have two vectors that lie inside the plane, right? I have X sub U and I have X sub V. And so we know that we can find a vector perpendicular to both of those just by taking that cross product. And so what we're actually going to do is we're going to, oh no. And so what we're going to do is we're actually going to take X sub U cross X sub V, and let's get a different color for this maybe. We're going to take X sub U cross X sub V, right, at this point in question, and the result is going to be a vector that is perpendicular to both of those, and therefore completely perpendicular to the plane. It will point up in that direction there. And so that gives us a perpendicular vector, or a normal vector. And if we want to create a unit normal vector, which we're often very interested in, we will just take this and then divide by the length. So we'll normalize it. So we'll end up getting this expression here, x sub u cross x sub v divided by the norm of xu cross xv. This will give us that perpendicular vector of unit length. And so that motivates the following definition, which I think comes very naturally. If we have a parametrized surface, we have a point Q that's in the domain space, right? So Q is a point in UV space, and x of Q is our point on the parametrized surface. That's our point P out here in three-dimensional space. Then the normal vector, which is computed as taking x sub u cross x sub v divided by the norm of xu cross xv, is the vector that is normal to the surface, aka the normal vector at P. And it should be stated here that the fact that this is a unit normal is implied. So if I want to emphasize that, I will also call this the unit normal vector. So notice, right, this says that it is a function of Q, and it really is. It depends on the point Q. In other words, for every point in the domain, for every point Q, I can go on to compute x sub u of Q, x sub v of Q, this cross product, this norm, and so I can compute the normal vector at every single point in my domain. Of course, the image that we have is sort of like a porcupine, right, where at every single point in the image, we have a slightly different unit normal vector, right? So this is sort of like a vector field on the surface of this parameterization here, right? But it's being computed at our point Q in the domain. Now, we spent the last video talking about change of variables. And so we've now been talking about several different things that we can compute, the x sub u, the x sub v, and now this unit normal vector n. And we should ask the question, what happens under change of variables to these different objects? Right, so here's a setup. Right, suppose we have, this is very much the same picture that we had last time. We have a map x that's mapping this point Q to this point P, and I can calculate the x sub u, the x sub v, and then the unit normal vector n, which we said would just point up in this direction here, right? So that would be my unit normal vector n, computed as the cross product of those two vectors, x sub u and x sub v. Now, we can ask the question, what happens if I want to change variables, specifically by taking a new set, say this set v, and taking a diffeomorphism f, right? So f would be a diffeomorphism that maps this set here into this set up here. And let's say specifically that it maps this point down here, this Q prime, to the point Q. Well, now I have a new parameterization of this coordinate patch, right? I now have not just this x, which maps this domain to the parameterized surface, but I actually have the composite map x of f, right? X of f that maps this space through this roundabout way to this coordinate patch. And there's this question of how does that affect our potential computations? And so let's take a look here. Right? So just like before, I can consider taking a derivative at the point Q, or I guess Q prime, in the horizontal direction and the vertical direction, what we were calling the u and v directions. So I can take a derivative in that direction, and I can take a derivative in this direction. And under this composition, we will end up getting a new vector up here, not necessarily the same two red vectors that we had there, right? This was x sub u and x sub v, but it's possible that this vector, or that taking a derivative in this direction, corresponds to a vector over here that's slightly different. Maybe it corresponds to these two vectors, and those will correspond to potentially two different vectors up here, maybe something like that and that. So two different vectors up here. So our diffeomorphism has the potential to change our x sub u and our x sub v into something else, into something different. But those two vectors will still be in the same tangent plane, right? They'll still be tangent to the surface, and so they'll still describe the same tangent plane. So under change of variables, our x sub u and our x sub v might change, but the underlying tangent plane, the TPS, will not change. At the same time, I can think about the unit normal vector, right? I would get that by computing the cross product of these two new blue vectors, and the result would be a potentially new vector, but when I divide by the length, when I normalize it, I should end up with one of two options. Either I get the exact same vector from before, still perpendicular to the surface, still with unit length, or I get the vector of unit length pointing in the opposite direction, right? And it will just depend on whether my cross product and my right hand rule push this vector to be pointing in the same direction as before, or possibly in the different direction from before, right? But in either case, we'll end up with a unit normal vector that is either the same or exactly opposite of the previous one.